Okay, well, thank you much for joining the meeting, and there is a knowledge transfer session on bringing the skills for non-adiabatic coupling dynamics into the domain of calculations with spin orbit coupling. So this has chance to enable broader range of systems that were forbidden for description in the previous. Oh, hello, Fatima. I see you connected. So these things were not available. There are several things that are not available in singlet or spin polarized DFT. Specifically, we were not, without this non-adiabatic coupling, one cannot describe spin flip transitions and reactions when the multiplicity of electronic state experiencing changes. So it is important for magnetic materials, for heavy elements, and for radical chemistry. So here is the little plan. Yvonne will cover molecular dynamics, not regular molecular dynamics because it's quite trivial, but the excited state molecular dynamics. Then Aaron will give an overview how to compute non-adiabatic couplings in presence of spin orbit coupling, and then David will give an overview of how to utilize these files towards obtaining electron dynamics and how to locate where to take these files from if they were not communicated to you by email or if you never did it before. So from this, let me invite Yvonne to the stage to present. Yvonne, if you like to share screen, you're welcome, but otherwise I can flip slides and just tell me when, whatever is your preference.
I guess you can show the slides.
Okay.
Okay, so in this slide, I show some difference between standard molecular dynamics in-car and TD-SME in-cars. So for TD-SME calculations, we need two in-cars. We need an in-car wall and the in-car excited. So,
wait, may I ask? I have a black screen. I don't see anything appearing on my screen. Is it only my problem?
I'll visit your office. Oh, let's ask everyone. I see things on my screen, but maybe
I can see my slides.
I cannot see. Maybe I do. Second.
There are two. You can either bring everyone's faces to the enlarged mode or the shared screen.
Okay. I think I found it. Yeah. Okay. Sorry about it.
Okay, not a problem.
Okay, so for TD-SME calculations, we do not specify temperature in cars because we believe the accumulated kinetic energy is solely due to the optical transitions.
Mm-hmm.
So here is temperature is 0. We also need to keep the wave car and the charge car. So this is important. And we need to set the S mirror equal to -2. So this tag allows us to specify electronic configurations for each orbital. And SW equal 5, this means we do nuclear movement for 5 picoseconds. And we specify the number of bands, and we use Fourier to control the electronic distribution. The following is just a standard setup for non-collinear calculations. So in the right, I have a movie which show the trajectories about for electronic modes excitation for last night cycloquantum diurnal complexes. This is about 2.5 picoseconds trajectories. I guess the problem is, according to this study, we find that the accumulation of kinetic energy in TDSM calculations with non-collinear setup is not very efficient. Because previously we do our TDSM calculations in spin-restricted setup, and we find the vivid reaction events in about 1 picosecond.
But for adequate comparison, were you taking the corresponding transitions at the similar energies and adequately strong oscillator strengths?
Yes, other parameters are almost the same, I guess. I'm not sure about the oscillator strength, but it's among the bright transitions, and also the excitation energy is pretty similar.
Okay, okay. And it looks like the main step forward in this slide, it is a confirmation from Yulun that setting up Fermi weights, resetting the occupations of the orbitals is available under non-collinear spin. And it is much easier than in spin polarized. Like in spin polarized, one needs to set up a list of two strings of numbers for alpha and beta, and here it is a single string, and according to Yulun and this data, it seems working fine, right?
Yes.
Okay.
So next slide, please.
And in order to run, you show it here. Yes, sorry. Please keep going.
Yeah. To run our TDSM calculations, we need a special script. And this is the main part of the script. So basically, it has two blocks. The first one, we do excited state molecular dynamics. And for the second one, we do bound state molecular dynamics. And so these two parts will be considered as a Rabi cycle. So basically, for very small or simple system, we probably need 100 Rabi cycles for spin restricted TDSM calculations, and we probably need 200 Rabi cycles for spin polarized TDSM calculations. So, and also in this file, we save a lot of informations. For example, we save the final geometry in each part. We also save the trajectories in XYZ format. We also get some key information like the total energy, temperature, something from the orbital.
I have a question, very brief one, technical. In some of the scripts to run VASP jobs on NERSC, one needs to request the load of the module, like to load libraries like module, load VASP. And in this script, it seems missed. Is it loaded by definition, or one needs to type some specific commands before submitting the script? Or it will recognize this VASP NCL executable immediately?
I guess the line is just consistent with our regular molecular dynamics calculations. That's the reason I do not put it here.
Okay, but in order to make it run,
yeah, we do need a line to load the VASP first.
Okay, so there is in order to make the script active, one needs to put one more. It's only non-trivial part of the script, but there should be at least one or maybe more lines added.
Yes.
Okay. Okay. clear. Thank you. And just as a bringing to attention of all audience, the most important difference that we were highlighting on the previous meeting a week ago. So here, looking from in the red box, third line from the top, S run minus N 64 VASP NCL. So for non-collinear spin, one uses different executables. So manipulations with in-car without using different executable will lead to an error instead of interesting results. So it is different executable compiled separately, and it's just a couple of letters in the name, but it is a critical point. Okay, sorry for interruption. Please keep going.
Okay, next slide, please. I guess here I just show some example about the TTL file. So this one contains several information from OZCar, and we can just get different kinds of information from it. For example, I show the right one, the bottom right, bottom left. Here I show the temperature along the TD-SMD trajectories. We can see the temperature increases linearly, and also we can see the changes of total energy along the TD-SMD trajectories. And bottom right shows the magnetic moment along the trajectories. From top to bottom is XYZ component.
Is there a way to look at the total magnetization? Is it available in VASP, or one needs to write a little code to make mz squared plus my squared plus mx squared?
Yeah, I'm not sure if it is available in the old code.
Okay.
But
okay.
in the old code, I did not find it.
Okay. So what? Magnetic moment. Yes, one would probably need the total magnetic moment to be able to identify if at the certain time step system is in the singlet, triplet, doublet, or any other multiplicity. But this red, green, blue components definitely show that there is some change in the spin multiplicity. Okay. Is it everything, or there are more comments?
That's it.
Okay. Please join me in thanking Yvonne. It was brief but very important. So if anyone is looking forward to practice excited state molecular dynamics with spin orbit coupling, please contact Yvonne for details.
I have a question.
Please.
May you go to the first slide with some settings for your input file?
Uh-huh.
Yeah. So TEFEG, I guess it's temperature beginning, temperature end. It's equals to 0. What does the settings mean, and why is there 0? If the space for the temperature, why your dynamic is at 0?
Yeah, that's our assumption, because we believe the kinetic energy accumulated by the system is due to optical transitions. So we do not introduce external like trigger to system.
But your system is not at zero temperature in the beginning. I mean, if you simulate it for real systems, probably the experiment is taking place at 300 Kelvin.
Yes, that's right. So basically, for our simulations, we use geometry optimized model as a starting point. In this way, like we artificially delete the possibility of room temperature configurations.
But then, you use these parameters to calculate non-negative couplings as the next step?
So this is a problem we need to address in the future. But right now, our assumption is because the optical transition is very intense. So the probability of electronic transitions induced by optical field is much stronger, or have much higher probability than electronic interactions with lattice with photons.
I'm just wondering, where's the Ibrahim in this case?
What is what?
Ibrahim? I mean, Ibrahim keyword?
You need Ibrahim for set up the dynamics, right?
Yes.
There are several ways, 1, 2, 3, it's defined different algorithm and different approach to the dynamics. So are you having this Ibrahim to whatever value and you know what is it?
I remember it's 2, I guess. I need to double check.
Yes, it is 2. It is 2 for molecular
So
dynamics.
Is it the same as we regularly use for the dynamics, molecular dynamics?
Yes.
So 2 is not a dynamics. 2 is calculated in the Ibrahim 2, T back equal by default 0. So it doesn't count the T back keyword. Because in Ibrahim 2, it doesn't apply any kinetic energy to the ion. I'm not sure if I'm right. Am I right, Dimitri?
Let's double check. We can open the in-car and say, but it is the standard molecular dynamics with the only changes that differ, only the differences from the standard molecular dynamics with micro canonical ensemble are shown here. So, Elon, is it correct?
Yes, we just use the standard molecular dynamics info. So we
Okay.
need to double check the tag.
Mm-hmm. So it should be Ibrahim 0, and
Ibrahim 0, yeah.
The also there is a little, I wouldn't say confused, but detail that needs to be brought in. I'll just make an empty slide and just scratch couple of quick notes. So regular molecular dynamics that will be followed by electron dynamics is started from thermalization. The procedure for excited state dynamics corresponds to several cycles by optical excitation, and this dynamics is different. So what Yulun was talking is about is TDSMD, so time-dependent excited state molecular dynamics, which does not start from room temperature. So it starts from temperature equals 0, and then it accumulates temperature due to difference in potential energy surfaces of ground and excited states. So it is two different stories. So for molecular dynamics with spin orbit coupling, one may expect that it will be slight changes, but it was not explored what would happen if one just enables spin orbit coupling and run plain molecular dynamics under initial heating. There is one more comment. If one uses this Ibrion zero, if one uses standard molecular dynamics, the temperature tags here do not relate to the kinetic energy of nuclei. They would correspond to smearing of the Fermi distribution. But here the Fermi distribution is set up explicitly. So this tag needs to be removed in order to avoid the conflict. So there is electronic temperature and nuclear temperature. And here those tags are for electronic temperature, which are not needed because Fermi distribution is set up explicitly. Yulan, please confirm or correct me if I'm misinterpreting. Okay. So let's call for more questions to this presentation. More questions one. More questions two.
So,
yes, Jabit?
yeah, just quick, just clarify the free V keyword. So is it means there are a 163 unoccupied band and the luma is 1? Is it right? And peaks 0?
Homo is 86.
Okay.
So the total band is 256.
So the occupancy of luma plus 7 is 1, is it right? So luma plus 6 is 1. In excited state in current, I mean.
Yes.
Mm-hmm.
Oh, okay.
Yeah, this string is used to replace long literal and explicit writing of 11111 80 times, then 0, then several 4 times 1, then 6 times 0,
Yeah.
then 1, yeah, and then zeros again. So
okay.
More questions? If no, please join me in thanking. Yeah. Jabit, you have.
I don't know what the keyword is. As the XIS, what is this keyword? I can Google it though, but I'm just wondering if
it's just for non-collinear calculations.
No, okay.
So it's you need to determine orientation of axis in space, because Cartesian axis and magnetic axis do not need to coincide. There is no theorem for their coincidence, and magnetic axis is needed to define where will be magnetic projections for x, y, and z. And here, through this s-axis, one sets up that they would z projection of magnetic field and z projection of Cartesian system of coordinates coincide. Without this being said explicitly, it would be not possible to interpret projections that are shown in the last slide. So, and any corrections to whatever I answered will be appreciated, if any. Okay, let's try once again. More questions 1. More questions 2. More questions 3. Okay, please join me in thanking Yulan once again. And the next presentation is by David. So David, you are invited to the stage. I will be happy to flip the slides, but if you want to, if you are in the mood to share the screen, let me know it.
Next.
Yeah, sure.
I mean, it makes more sense for Aaron to go first, but I will.
Okay, so stage is yours.
So, what I'm looking, showing.
Wait. Yes, yours is next. Yes, I was. I apologize. I was thinking about different things. I apologize once again. Next presenter is Aaron, because otherwise it doesn't make sense to analyze data that haven't been computed yet. Yes, Aaron, please start the story and unmute your microphone.
Okay, so I guess the most competitive computations that we do are dynamics. And to do dynamics, we have to compute non-adiabatic couplings in VASP. And I guess that'll be kind of just going through the scripts that are needed to compute these couplings. So next slide. So there are two categories of things that you need for when you do these calculations. So you need various text files, so input overlap, which we've covered in a couple of previous meetings. That just gives the range of orbitals to compute couplings that we care about, so usually within the range of the band gap. Need these PXXX files, which you make during molecular dynamics trajectories. And there's a, I don't think we've covered it, but there is a BTS script, which will make those from the XStat card, from wherever you did your molecular dynamics.
Aaron, would you please type the name of this VTST script in the chat line to make it a complete story? Or maybe during the question and answer session, because in order to reproduce whatever you instruct, one would need the script, right?
Yes.
Okay.
I believe what I put in the chat is what it's called, but it's converts XDOT to postcard files.
And does it work for the recent version of VASP? Does it work for non-collinear spin?
Yes.
Okay.
For molecular dynamics, we usually just do spin polarized or spin restricted. Well, that's not an issue.
Okay.
And then the way that I do these calculations, I keep two sets of NCAR files for the calculations. So the first is NCAR for spin polarized or spin restricted calculations. And then a second NCAR, which runs the non-collinear calculations. And I've got some examples of those in the later slides that I'll go over. And then there are 4 basic scripts that you need. So There's a query script, which is just the submission into the queue. There's a B script, which gives the instructions for to generate the couplings. Read wavecar healthy, compute some oscillator string files, and then a spinor.exe, which computes the oscillator strings and couplings. And so I guess we can go to the next slide. Then these are just the locations for the scripts that I'll be going over. And they're all in the bin on nurse, is where this bin location is. Next slide. So just to be thorough, so for usually my workflow for computing couplings that have spin orbit coupling involved, I've found that it's the jobs run healthier and quicker if you supply like a pre-converged files, like the wavecar, charge car, into non-collinear calculations. So for everything that we do, I first compute charge cars or wave cars from a spin restricted or spin polarized in this case. So the main things that you just want to remember is if you're doing polarized, have I spin equals 2, and then make it a single point calculation. So NSW is 0. And then I'll also note that it's sometimes helpful to explicitly say like how many bands are in the calculation and how many electrons are. Because for non-collinear, everything becomes singly occupied. So I guess to show this, in this case, n bands is equal 1920. And if we go to the next slide, the n tar for the non-collinear, so the number of electrons stays the same, but we have to increase the number of bands by 2-fold. And so if you just manually put those in, you have less chance of VASP getting confused and quitting the calculations. And then the rest of the NCAR is essentially the same. So we still run a single point calculation. So NSW is 0. And you basically just include the tags which tell VASP to run non-collinear and spin orbit couplings. So that says L non-collinear is true, LS orbit is equal to true. And then to have VASP read in the pre-computed charge car, that's what this I charge equals 11 is.
May I ask?
Yes.
So what would happen if one misses or comments out this L non-collinear equals true?
So I think L, like just with LS orbit equals true, that should automatically kick on L non-collinear is true.
So if by some reason I forget or intentionally miss this L non-collinear true and redo the calculations, I will get the same result if LS orbit true is there.
Yes, it should still run everything correctly.
Okay.
But I put it in just,
okay.
That's what I've always done, so I just superstitious.
Yeah. It's a healthy approach of a programmer, not to remove good things from the code. Okay.
So then those are the input files. And then next slide. So now we're transitioning to the scripts that we use to generate couplings. So this is the submission script for the Keylon Corey. So essentially, this is everything except the bottom line is standard for what the submission scripts look like. But instead of telling Corey to run a vast executable in the last line, we refer to run this B script .sh in the bottom. And then that leads into the next slide. Yeah, this was the question that I think Dimitri was asking before. So that's where load vast comes in. And then you tell Corey to look at this bscript.sh, and that's this line of text that's shown on the left. So essentially, it's just instructions to generate wave cars and then compute couplings, and then save various auxiliary files. So next slide, we'll focus on these top two paragraphs.
And the which one is, may I ask? So which one is more important, oscillator strength spinner or spinner.exe? Are they interchangeable? Can one survive if one misses one of them, or the equivalently needed?
I think they're both needed, but if it was needed, it would be possible to change the spinner script. But the reason I keep both is that if you want oscillator strings for every time step, like this first step that does like just one calculation, so it generates one wave car at, in this case, time is 0. Then it generates just the oscillator strings for time is equal to 0.
You can do it without the oscillator string spinner. It just won't give you the oscillator strings for every time step then.
Okay, yeah, thank you, David. There was a paper by Alexey Akimov in 2014 that we were discussing on the group meeting, and he was doing an image like a bookshelf with like books standing there, and considering the these books like time slices, and then making a comparison between time slices as couplings between different time slices. So therefore, the number of files for couplings is one less than number of time steps. Like if there are 3 time steps, there will be 2 couplings. If there is a 1,000 time steps, there will be 999 couplings. And this oscillator strength spinner seems to add additional calculation to complement it. David, I see you were saying something, but it was not. Was your yes? No? Do you need to put your microphone? Okay. Yeah. Sorry for interruption, Aaron. Please continue. Yeah.
In the loop, you are using the West gamma. I remember last time you told, I guess, David told the West gamma is not available for this kind of calculations. We should use West standard.
Yeah, so there are So there's different ways to do it, but the standard will read in a wave car, or NCL will read in a wave car from standard, but NCL won't read in a wave car from a gamma calculation.
Okay, so if you are importing charge distribution and wave car from spin polarized calculations, then it is mandatory to have VASP standard in these preliminary steps.
Yes.
Okay.
So is the VASP standard is running for only to create the web car, or does it have any other purpose?
No, the calculations tend to run quicker, or you get quicker convergence if you run like a pre-made charge car or wave car. You then feed that into the non-collinear run. So essentially, you just do a single point to generate like an input file into the non-collinear run. In principle, you don't have to do it, but I found that I know there was at least one model I was doing where it's after 50 time steps, it wasn't getting anywhere close to converging. It's doing MCL.
Okay.
Just to comment on what Yuan was asking, the in-car for the spin polarized for this one is actually set up not to write a wave car anyway. So the standard versus gamma wouldn't really matter much for this situation.
Okay. If there are no more emergent questions in the middle, let's continue. And if Aaron is in a good mood, let's continue.
Yeah, I guess we can go to the next slide.
Okay.
So these are just the top block of rows zoomed in so I can make some comments. But just for troubleshooting purposes, you want like these red boxes. Those are like the amount of resources that are requested. You want to make sure that you don't request more resources than you requested in the core submission script. So that's why I highlight these here, because that's something that can get overlooked. And then, essentially, these top 6 rows run the VASP calculations, and then these bottom rows just save the output files, where it generates oscillator strengths for this calculation, and then I also save the out car and the OSI car for each time step for future processing. Because the OSI car would contain like the magnetic moments that Yuan was talking about previously. Then the out car contains band energies. So that we can make those fluctuation figures.
Okay. Quick technical question, if I may. The 4, 5, and 6 from the bottom shows move oscillator strengths VC, CC, VV. Would you please comment on these notations and why they are needed?
So V stands for valence, and C stands for conduction. So we could have three possible transitions to look through. So we can have valence to conduction band absorption. So that would be interband. Or you could have intra-band, which would be like conduction to conduction transition, or valence to valence transition. So if you're looking for infrared absorption,
in the excited state?
in the excited state, yeah,
Uh-huh.
you look at these CC and DVs. But most of the time, we're mostly concerned with these VCs.
Okay, yeah, thank you.
And then the next slide. And then this is just looping through all the PXX X files or postcard files, and then just running vast calculations to make wave cars that we compute non-adiabatic couplings with. And that's what this spinner.exe script does.
Okay.
And then depending on the system size, it's like I set this loop for 1 to 50, but usually, like, for the systems I look at, like I might get 10 couplings done. So then you just have to be like,
Are we still connected? Are we still connected? If no, let me
I can hear you.
Yeah, I can hear you too.
Oh, okay, okay.
I hear you as well.
Maybe
Aaron?
Aaron, do you hear us? Okay, but I believe we have. It was the last slide by Aaron. Let's give a round of applause to Aaron just in case, because it was really a helpful and useful presentation. So if there are any questions and Aaron will come back, he will answer. If no, I can try answering on behalf of him. And the practically most important thing is this couplings files that this dollar $J will mean that there will be a set of files, couplings point, and then running with the numbers that are set up in the beginning of the line, like 0, 0, 1, coupling 0, 0, 2, coupling 0, 0, 3, and this and so forth. So this set of couplings, each file with such name is a matrix with rows and columns signifying the orbitals and the amount of orbitals in the list. The amount of the orbitals used in this coupling is the same as we use for computing oscillator strengths. So it is specified in the input overlap file, and it shows from first orbital, like initial, to the final, and then each coupling files is a matrix where rows and columns run from orbital initial to orbital final on rows and columns, initial, final, and each element inside this matrix corresponds to rates of transition from orbital I to orbital J. So as a main output of this calculation, one is getting like as many matrices, as many steps, time steps along the trajectory one has requested. And to go to the next step, one needs to download these files from the cluster to the local computer, where one needs to have MATLAB installed. And in order to go to dynamics of excited electronic state, one needs to convert these couplings files into form of so-called Redfield tensor, which means averaging of these couplings over time steps. Before we give stage to the next speaker, so according to Alexei Akimov, these couplings are here, so long time steps on the trajectory for each pair of electronic structures at time steps. There is one coupling file. Okay, if there, I don't know if Aaron did reconnect back. I do not see him in the list of connected. So if there are questions to Aaron, please type or ask them. We will either try to discuss and address or forward them to Aaron when he's available. There is a typed question from Yoon. He's asking if S-axis tag is required for in-car NCL. I believe calculations will go without this tag as well, and there will be no error. But if one needs to analyze the magnetization, and if one probably is looking onto magnetic materials or looking in the future to describe NMR signal where orientation of the magnetic moment in respect to orientation of the system is important, it makes sense to add this. But if one is looking only for transitions between electronic states, maybe it is okay to skip it. Are there more questions to Aaron and his presentation? If no, we forward our round of applause to Aaron.
Yeah.
I hear some voices. Oh, it was applause. Okay. So, and the next presentation is finally by David Graupner. So, David, please unmute your microphone and take the stage. And sorry for inviting you to present earlier. I was thinking about something different, or really wanted to hear your talk.
So what I'm going to look at is analyzing the coupling data that Aaron just showed us how to make. and the next slide. So the first thing that we're going to need to do is we're going to need to create our input files that we need to do our electron dynamics, photoluminescence, and the like. And for that, we need a correlation.m file, and that's the MATLAB code we're going to use for this. We also need the energy pop file from our calculation that we did. And we're going to need all the coupling files that we generated. And off to the side here, I have an example of the correlation.m file. And I have boxed some of the things that you're going to need to check and alter based on your model. In the red box, I have the HOMO, the OMIN, and OMAX tags, and what those are is the HOMO and the highest and lowest bands that you're looking at. In the green boxes, I show the number of coupling files. So you need to enter those into there. And in the situation, I show we're going up to 1,500 coupling files. And in the blue box, we have a couple different instances where we analyze where we show the number of steps that we take. And if you notice, I didn't highlight it specifically, but there's 1,500s in that box. You generally want that to be equal to the number of coupling files that you have.
May I ask?
Yep.
So as an introductory step, would you please comment on similarities and differences of this calculation steps that you're going to overview in comparison to singlet situation when one doesn't have any spin polarization and any spin orbit? Would it be correct to say that computational procedure is completely identical to what one would do without any spin? Or there are any changes, or one should look at some details?
It is effectively the same. The major difference is the way that spin orbit coupling handles bands. So in spin restricted, you have 2 electrons in each band, where in spin orbital you're going to have 1, and every band is going to have 1. So this, what I have circled in the red box, is double what it would be if this was a spin restricted calculation.
Okay, so one cannot blindly copy paste these modifications to the code from spin restricted to non-collinear spin, but other than these parameters, the structure of the code is the same.
The structure of this code is the same.
And I'm bringing it up because if one is going halfway only to the spin polarized calculations, then all codes are changed or substantially and drastically. And also, if one goes to the explicit account for momentum dispersion, the structure of the codes differs because one needs to explicitly follow several threads for different spins or for different k-points. But here, due to the eigenstates in this spinor representation picks both alpha and beta components and intermix them, it creates absolutely great framework to describe advanced concepts on the so to say, simplified way. Yeah, sorry for interruption. Please keep going.
So then, once you modify these parameters for your specific model, you want to run your MATLAB code, which will give you an output file, which is the RRR file. If you want to go to the next slide.
Okay.
So our major output from this is the RRR file, and I have a visualization of the Redfield matrix here. And what this is showing is it's showing the relative rates that the electron and hole relax, right? There is an issue with the one I put on here that I didn't notice when I did it. So it's the one I have here isn't very interesting to look at, but
Dave, may I ask a question? So would you please comment if there are any additional files and any additional image windows popping up from this code, and what do they mean? Specifically, I want to ask you about autocorrelation function for given pair of orbitals.
So yeah, the autocorrelation function, we also get a graph pop up for that, and it looks pretty much like what you drew there.
And what is their significance? Can one completely ignore them, or what should I look at? When is the red flag? When one needs to be careful, and when one can ignore and skip them?
So the autocorrelation function, we're looking for fast, fast relaxation down to the 0 point. I think you have it marked here as delta t. And then it's going to oscillate along the 0 point for the rest of the trajectory.
Okay, yep. So if it decays quickly, then everything is good, and one may forget about it or not focus on it too much. Okay, let me know if you.
I agree.
Okay. When you are in a good mood to go to the next slide, let me know.
Yeah, we can go to the next slide.
Okay.
Unless there's more questions. So once we have our RRR file, we then need to run a different code to generate our electron dynamics and photoluminescent results that we're more interested in. So for this, we once again need the energy pop. And we also need the band out file, the RRR file, the fork master optics file, and a MATLAB script, which I have typed out the example, the one that I generally use for this. So the energy pop file is once again going to come from our calculations. The band out is matrix. No, the 4-master optics is a matrix version of the OS strength files. The band out is a, I can't think of what I'm looking for, is a not thinking of the word I'm looking for.
Just try a different word.
It's
or just show by hand waving.
It's one it's a one-dimensional version of the orbitals. It's a bad way to put it.
Okay, so maybe integrated orbitals?
That's the word, integrated.
Okay.
So then this one also has some parameters that we want to set. So once again, in our red box, we have the HOMO, the OMIN, and the OMAX, which are the same as they were in the previous example. And in the blue box here, we have our initial parameter that we're using. So we have IH in this case equals 6 and IE equals 11. And what that means is that we're exciting an electron from HOMO -5 to LUMO +10 as our initial condition. And one thing to check in the green box here, we have the Z size and the Z steps. The Z size should be the size of your cell along the Z axis, which you can get from your postcard, where the Z steps is the number of steps, which you can get from your band out, number of steps along Z, which you can get from your band out. So in this situation, I just randomly chose my initial conditions, but generally you're going to want to use ones that have a good oscillator strength. Because those are the ones that are most likely to occur. If I remember what these ones were, they were a moderate oscillator strength, but I don't have that file in front of me offhand. So then once you run this, you're going to get several different results. So if we go to the next slide.
Yes, may I ask before?
Yep.
So, are there any limitations that you see? Any specific situations when one should be hesitant to apply this set of codes? Here is my little concern. The energy pop and band out, which are list of orbitals and list of integrated charge distributions, are taken just once, while for substantially changing geometry, this distribution of orbitals may experience some variation. So in which situations it is applicable approximation to take just maybe average energy or first energy or set of energies or energy from relaxed geometry, and when it is absolutely not applicable?
So we do have a process to make a band out, a different type of band out. That is more, that works a little better for spin orbit coupling, but it is for this specific MATLAB code is not used, so I didn't include it here.
The question is basic. It doesn't deal with any modifications of the code. Like it deals with what you see in molecular dynamics.
So when there are big changes in molecular dynamics, this is going to be less of a good approximation.
Okay, so if there are phase transitions or bond breaking events, then this code would be not applicable. One needs to find some different.
Yeah. So okay. And that's where we would use the more precise bando, which is a MATLAB code in its own situation.
Okay. And I believe Aaron is back from the technical problem with connection is resolved. So Aaron, would you please confirm the question that we discussed with David? So some of the codes are labeled here, so that is version specifically edited for spin orbit coupling, but other substantial changes in the excited state dynamics codes with spin orbit and just for singlets without any mention of the spin. And if microphone is not working, you may just type in the chat room.
In principle, they're basically the same.
Okay.
In some situations, you might need some slight modifications, but that's more system dependent than with the code itself.
Okay. Okay. And when we will go through David's presentation further, at the end, there are some links to versions of the code. If you identify that the examples and templates of the code specifically edited for spin orbit are missed in the repository, would you please upload some template and share the link in the chat line?
Yeah, are they all on NERSC?
Yep.
Well, the ones I can find are on Photon.
And there are on NERSC as well. But let's return to this question when in like in 3 slides.
Okay.
Yep. Sorry, David, for interrupting you in the middle. Please go forward.
So if we go to the next slide, we can see some of what we get as an output. So we get our relaxation rates, which are which will pop up when you run MATLAB. So in this situation, KH, which is the relaxation of the hole, is 0.93, and KE, which is the relaxation of the electron, is 0.52. And off to the side here, I've also put in a waterfall graph of the occupancy of our. So yeah, the line you just drew would be KE. There's a corresponding one on the blue for KH, or 1 over.
Mm-hmm.
So we have a waterfall graph of our occupancy, and this is the occupancy for the hole.
Mm-hmm.
So we can see that it starts with the hole in 6 and eventually goes to where the hole is split between the HOMO and HOMO minus 1, which are the same and which are degenerate in this model. And And the green graph here is a energy versus time, showing the relaxations of the electron and hole. So we see that around 1 picosecond, both the hole and the electron relax. You could also do position versus time. I did not readily have that graph available to add to this slide.
So the following was not the main goal of your talk, but would you please give a brief explanation of the color code and content of this greenish figure?
Yeah. So the green is the background. It's 0. The yellow is the energy of the electron. So it starts out around 3 eV, around 1 picosecond. It drops to approximately 1.5. But we see, and it's best highlighted in the expectation value, which is the dotted line here, that there is some continuation of the energy around 2.8 or so that continues for basically the entire run that I made this graph. And the blue is the hole, and it's the same basic principle. We see that our initial excitation, our hole is initially at about -2 eV, and then ups to -1.8, around 1 picosecond.
Would you please navigate me where is HOMO and where is LUMO on this graph, and where is the band gap?
So HOMO and LUMO are going to be the final final values, so approximately 1.7 and -1.7. So there's about a 3.5 eV band gap for this material.
So at the end of the dynamics, electron hole settle on the HOMO and LUMO at the lowest possible excitation.
Settle on the HOMO, LUMO, or LUMO +1 or HOMO -1 as they're degenerate in this model. And we talked about that earlier, where we may need to factor that into some of our photoluminescence calculations. We were talking about that the last time I presented a month or so ago.
And this approach would work for any number of electrons, even if and any multiplicity. Okay.
And in the next slide, what I am showing here is the photoluminescence result from this model. And we see that we get the major peak right around the band gap, which is very hard to read on this model, because apparently I made it too small. And then, yeah, so it's a little under 3.5 there. But and then on the right, we have the intensity of our photoluminescence with the peak, the really big peak there at 0 is a artifact of the code because they're degenerate. And my belief on what all the peaks we see in the intensity below the band gap are interband interactions, because we can see that some photoluminescence above the main peak, which, if you look at it, appear to be similar in energy. If we were to calculate from those to the band gap, they're both similar in energy to what these are.
So those are transitions inside the band, right?
Yeah, so those would be intraband.
And would it be correct to say that they correspond to oscillator strength CC and oscillator strength VV that Aaron was presenting?
Yes,
okay.
I would, based on what I would assume they're probably CC primarily, but I honestly would have to look at the oscillator strengths for the intraband interactions closer than I have.
Okay.
So then in my next slide is we start getting some of the locations for these, and they're found in the bin. And
okay, so there is a correlation to generate RRR, and there is
so there's a generate RRR, and in the chat box I just typed in a location in the bin, and this is, as far as I can tell, only on the photon. It's not on NERSC. That
okay.
have some of the MATLAB codes we need in it. I for one cannot find the specific code I was using in MATLAB, or not MATLAB, in NERSC or Photon. It was emailed to me.
But can you just, I suggest either you or Aaron just upload or make another.
I can add it, but
yeah.
Just as of right now, I personally can't find it. If it's there, I don't know where it is. But yeah, so we have several different.
But David, you can just upload the codes that you are using for your own purposes. Okay. Aaron, would you please check if the files there seems reasonable, and if you want to add any other, to share some templates of the codes?
Yeah, I have a couple of versions I can put in.
There are a couple of maybe the same versions as on Photon on NERSC, but I do see that they do not have this SOC tag, which probably means that these versions were not updated, and even if the changes are minimalistic, it would be better to have most recent codes templates shared, so that any of visitors, attendees, collaborators can try their luck to use it. Okay, David, is there anything else in your presentation that, or in your thoughts that you wanted to share?
Not really, unless there's some questions from someone.
Okay, then I invite everyone to join me in thanking David for important presentation that shows a way to describe electron dynamics and photoluminescence in the system where spin may eventually flip. So this is important for radicals, metal-organic complexes and magnetic materials. So if Steven is here, this method could be very useful for predicting emission of metal-organic complexes. Okay, let's check if there are questions specifically to David or maybe to anyone in the audience, any points of discussion. So more questions 1, more questions 2, more questions 3. Let's thank David once again. And with this, we are completing the summer schedule of the group meetings. I hope that recordings went well and it will be eventually shared with all attendees. Let's put at least next week as a little vacation from presentations between semesters, and then we will set up the meetings for the schedule of the meetings for the fall semester, which could be on the different link and maybe different facility like Zoom instead of joint.gov.nd. So if you are already in the middle of some projects with spin orbit, then it is super. If you are not using spin orbit coupling, please review if it could be applicable to your case, and feel free to contact the authors of today's talks and try to use the suggestions or the quotes. So many thanks to all participants for productive summer and very inspiring meeting. Meeting is done. Everyone is welcome to depart. Not depart, disconnect. And I'll stay here just in case if there are more questions to discuss. Thank you, Ewan. Thank you, Aaron. Thank you, David. Yeah. It was nice seeing you here, Steven, Amir, Fatima. Oh, Raju, I'm happy to see you. You put your camera on.
Yeah. Thank you.
I'm